There's a rule in astrophysics that everyone trusts. Distance equals safety. 200 million kilometers from the sun? You're irrelevant. You're cosmic background noise. Except on October 29th, 2025, something broke that rule. An interstellar visitor named 3I Atlas reached Perihelion at a distance that should have made it forgettable, just another dot in telescope data. Instead, the sun erupted. A monster sunspot materialized. Earth's crust trembled with inexplicable quakes. The timing wasn't just suspicious, it was surgical. Could an object staying safely outside Earth's orbit somehow reach across the void and destabilize our star? Stay with me, because what scientists discovered about this visitor challenges everything we thought we knew about cause and effect in space. And the implications? Well, they're just beginning. Keep watching, because 3I Atlas is still out there, receding into deep space, and observations are continuing from telescopes tracking its every movement. Hit subscribe to stay updated on this unfolding mystery, because every new data release, every spectroscopic analysis, brings us closer to understanding whether this was just cosmic coincidence or evidence of interactions we've never documented before. So settle in and let's unravel this interstellar enigma together. October 29th, 2025. Mark that date, because on that day, something arrived at the doorstep of our sun, and nothing has been quite the same since. The object had a name that sounds like a government project gone wrong. 3I Atlas. The 3I means it's the third confirmed interstellar visitor we've ever tracked. A wanderer born in the cold between stars, now streaking through our solar neighborhood on a trajectory so steep it could only mean one thing. This thing came from outside. Way outside. It wasn't ours to begin with. At 1300 hours Universal Time, 3I Atlas reached Perihelion. Astronomers speak for its closest approach to the sun. But here's where things get weird. Perihelion usually means diving deep, getting cozy with our star, maybe even skimming the chromosphere like some cosmic daredevil. Not this time. 3I Atlas peaked at 1.36 astronomical units from the sun. That's 200 million kilometers. For perspective, Earth orbits at 1 AU, so this visitor never even crossed inside our planet's path. It stayed outside, aloof, distant. Under every law of physics we understand, that distance should mean absolutely nothing. Gravitationally, you'd need to be orders of magnitude closer to tug on something as massive as the sun. Electromagnetically, the inverse square law is brutal. At that range, any charge or field this object could carry would dissipate into background noise long before reaching our star. This should have been a non-event, a celestial near miss that we'd catalog and forget. Except the sun didn't forget. Within days of perihelion, something monstrous was born on the solar surface. Astronomers cataloged it as AR4294, an active region that grew into one of the largest and most violent sunspot complexes observed in recent years. We're talking about a magnetic knot the size of several Earths, crackling with energy, spewing X-class flares like a malfunctioning reactor. The timing was immediate. The violence was unprecedented for this phase of the solar cycle, and it was facing us. Now you might be thinking, coincidence. The sun's a temperamental ball of plasma. It has moods. We're currently in solar cycle 25, approaching solar maximum when activity naturally peaks. Sunspots happen. Flares happen. This is just stellar weather doing stellar weather things, right? Maybe. But consider the timing. Consider what else happened. As AR4294 roared to life, seismologists around the world started noting something unusual. Reports of earthquakes spiked. Not catastrophic events, not magnitude 8s tearing cities apart, but a pattern, a clustering. small to moderate quakes in regions that don't typically shake and sink. The United States Geological Survey logged the data. Independent monitoring stations confirmed upticks. Social media lit up with people reporting tremors from disparate locations within the same narrow window of time. Correlation doesn't equal causation. Every scientist knows this. Every rational person should know this. But when two seemingly unrelated phenomena occur in lockstep, when a distant object times its closest approach with solar chaos and terrestrial unrest, you start asking questions. Uncomfortable questions. Could something 200 million kilometers away reach across the void and short-circuit our star? Could it somehow whisper to Earth's crust through mechanisms we don't yet understand? The official answer from NASA, from ESA, from every credible space agency is simple. No. The distances don't work. The physics don't work. This is coincidence dressed up as causation by pattern-seeking human brains, desperate for narrative. But here's what makes this story fascinating, what keeps it alive in the minds of researchers and conspiracy theorists alike. We have images, real data. The European Space Agency's JUICE spacecraft en route to Jupiter captured 3I Atlas during its Perihelion passage. The Hubble Space Telescope trained its aging but still sharp eye on this visitor. Mars orbiters caught glimpses as it passed, and what they saw challenges some assumptions about what interstellar objects should look like. This wasn't just a rock, it was active. Violently so. A coma of gas and dust enveloped the nucleus, streaming away in the solar wind like hair in a hurricane. Spectroscopy revealed carbon dioxide, water vapor, complex organics. The object was outgassing, shedding material, reacting to solar radiation in ways that looked almost organic, almost alive. And it brightened. Oh, did it brighten? As it approached the sun, 3I Atlas flared. In luminosity, far faster than models predicted. Comets brighten near the sun. That's normal. But this was different. The rate of change, the intensity, the sheer amount of material being ejected, all exceeded expectations based on its estimated size and composition. Something about this object didn't fit the standard comet playbook. So we return to October 29th, 2025. We return to that moment when an interstellar wanderer reached its closest point to our star and the sun erupted in magnetic fury while Earth trembled beneath our feet. We return to the question that nobody in mainstream science wants to touch, but that nags at the edges of every curious mind paying attention. What if distance doesn't matter the way we think it does? What if there are mechanisms, interactions, resonances in the plasma environment of the solar system that our current physics doesn't account for? What if 3I Atlas did something to the sun, and by extension to us? The investigation begins here, with credible data showing undeniable timing, with images from some of humanity's most advanced instruments showing an object that defies easy categorization, with mainstream explanations that feel just incomplete enough to leave room for doubt. Before we dive deeper into the weirdness of this object, before we explore the scientific disagreements and the fringe theories and the data gaps that keep this mystery alive, let's establish what we absolutely know for certain. 3I Atlas visited. The sun reacted with unusual violence. Earth registered increased seismic activity. The timeline is real. The correlation is documented. Whether causality exists between these events, well, that's the question we're about to spend the next several thousand words trying to answer. And I can promise you this: the deeper we go, the stranger it gets. Let's get to know our visitor. Because 3I Atlas isn't just some random chunk of ice and rock that happened to wander through. This thing has a pedigree, a biography that stretches back beyond the formation of our own planet. July 2025. That's when astronomers first spotted it. a faint smudge moving against the background stars in a way that immediately raised eyebrows. The trajectory was wrong. Not wrong like a calculation error, but wrong like it fundamentally didn't belong to our solar system's gravitational family. When you plot the orbit of any normal solar system object, planets, asteroids, comets, you get an ellipse, a closed loop bound by the sun's gravity. Maybe it's a tight ellipse like Earth's nearly circular orbit, or maybe it's wildly elongated like some long-period comets, but it's closed. The object always comes back. Not 3i Atlas. Its trajectory traced a hyperbola, an open curve that means escape velocity. This object was moving fast enough that after its brief visit to our solar neighborhood, it would slingshot back out into interstellar space, never to return. The orbital. Energy was positive. That's the mathematical fingerprint of something that came from outside and is leaving for outside. We've only confirmed 2 other objects with this distinction. 1i, Oumuamua, in 2017, that cigar-shaped enigma that sparked 1,000 debates. 2i, Borisov, in 2019, a more conventional-looking comet that at least behaved predictably. Now 3i Atlas, visitor number 3, and already it's rewriting the rulebook. Pre-discovery images push the detection back further. Astronomers love this game, scouring old survey data for objects that were caught on camera before anyone knew to look for them. 3i Atlas showed up in images from months earlier, allowing researchers to refine its trajectory with greater precision. The calculations were unambiguous. This thing originated from interstellar space, from the region between stars where temperatures hover just above absolute zero, and matter is spread so thin you could travel for years without hitting a single atom. What was it doing out there before it found us? How long had it been traveling? We can't know for certain, but we can estimate. Based on its velocity and trajectory, 3i Atlas likely spent hundreds of thousands, possibly millions of years, drifting through the galactic neighborhood before gravity's invisible hand bent its path toward our sun. Now for the physical description, and this is where things get interesting. The object possessed a coma, that fuzzy halo of gas and dust that makes comets look soft and approachable in photographs, even though they're anything but. Except this coma was particularly active. Spectroscopic analysis, the technique where we split light into its component wavelengths to identify chemical signatures, revealed an atmosphere dominated by carbon dioxide. Not water, which is what you'd expect from a typical solar system comet. CO2, with water vapor playing second fiddle, along with traces of methanol, hydrogen cyanide, and other organics. The James Webb Space Telescope, humanity's newest and most powerful infrared eye, trained its instruments on 3i Atlas during Perihelion. The data it returned showed emission lines consistent with complex carbon-bearing molecules. This wasn't surprising in itself. Comets often carry organic chemistry, but the ratios were off. The relative abundances of different species didn't quite match the patterns we see in native solar system comets. Then came the brightening. Comets typically brighten as they approach the sun, following predictable curves based on their size and volatile content. The closer they get, the more solar radiation they absorb, the more ice sublimates into gas, the brighter they appear. We have centuries of observations that let us model this process with reasonable accuracy. 3i Atlas said, "Forget your models," and brightened far more rapidly than predictions suggested. The luminosity curve steepened near perihelion, indicating either that the nucleus was much larger than initial estimates, or that something about its composition or structure made it unusually reactive to solar heating. Astronomers scrambled to recalculate. Was it 300 meters across? 5 kilometers? The uncertainty range was embarrassingly wide. But here's the truly bizarre detail. The observation that has researchers scratching their heads and writing careful papers hedged with caveats. Polarization measurements. When light scatters off particles, it becomes polarized, meaning the electromagnetic waves align in particular directions. The degree and direction of polarization tells us about the size, shape, and composition of whatever scattered the light. Every comet we've studied shows a characteristic polarization pattern: positive at certain angles, negative at others, following curves that vary, but stay within understood bounds. 3I Atlas displayed deeply negative polarization at wavelengths and angles, where it should have been positive or neutral. The measurements came from multiple independent observatories, ruling out instrumental error. The polarization signature was unlike anything in the existing database of cometary observations. It suggested either dust grains with very unusual properties, geometric shapes we don't typically see, or a surface composition that defied standard comet chemistry. One research team floated the idea that the dust might contain a high fraction of organic compounds with complex refractive indices. Another suggested fluffy aggregate particles with void spaces that scatter light in unexpected ways. A third paper, more speculative, wondered if we were seeing evidence of material formed in interstellar space under conditions very different from the solar nebula that birthed our own comets. The JUICE spacecraft gave us our best close-up looks. Even though JUICE is headed to Jupiter, not hunting comets, its trajectory happened to provide a favorable viewing geometry during 3I Atlas's perihelion passage. The images showed a comet that looked simultaneously familiar and alien. The coma structure, the way gas and dust streamed away from the nucleus, it all resembled standard cometary behavior. But the intensity, the sheer volume of material being ejected for an object of its presumed size, that didn't quite add up. Mars orbiters caught it too, tiny telescopic glimpses from the red planet as this interstellar visitor cruised through the inner solar system. Every dataset added pixels to the portrait, but the portrait kept revealing contradictions. The scientific papers are careful. They present observations, note anomalies, suggest possible explanations, and conclude with variations of further study is needed. That's how science works. You don't scream aliens or doomsday rock every time something doesn't fit the model. You refine the model. You get more data. You stay humble about the limits of your knowledge. But in the coffee rooms, at observatories, in the Slack channels of research teams, in the comment sections of preprint servers, a different conversation happens. Researchers admit confusion. They share the, that's weird moments that don't make it into published abstracts. They wonder aloud if maybe we need to expand our understanding of what interstellar objects can be. Because 3I Atlas looks natural. It has all the hallmarks of a comet: icy nucleus, gas coma, dust tail, chemical composition, consistent with frozen volatiles. But it behaves in ways that challenge the simple models built from studying objects born in our own solar system. It's brighter than it should be. Its dust scatters light wrong. Its chemistry is slightly off kilter. And oh yes, it happened to reach perihelion right when the sun decided to throw one of its biggest magnetic tantrums in years. That last bit, the timing, that's not part of the physical description. That's correlation, coincidence, the thing we're trying not to jump to conclusions about. But it hangs over every analysis like a question mark made of plasma and uncertainty. Welcome to the part where reasonable people disagree, sometimes politely in peer-reviewed journals, sometimes less politely at conferences after the third drink. Science isn't a monolith. It's a brawl of ideas where the weapons are data and the casualties are hypotheses that couldn't stand up to scrutiny. The mainstream heliophysics community has a straightforward explanation for the monster sunspot that appeared after 3I Atlas's perihelion. We're in solar cycle 25. The sun operates on an approximately 11-year cycle where its magnetic field completely flips, and during the ramp up to solar maximum, activity increases dramatically. Sunspots cluster, flares erupt, coronal mass ejections blast plasma into space. This is normal, documented, predictable, at least statistically. AR4294, the massive active region that bloomed on the Sun's surface in early November 2025, fits squarely within the expected behavior of a star approaching the peak of its activity cycle. Yes, it was large. Yes, it was violent. But we've seen comparable regions before. The Halloween storms of 2003, the Bastille Day flare of 2000, the Carrington event of 1859, which was so powerful it set telegraph wires on fire. The Sun is capable of tremendous magnetic violence all on its own, thank you very much. No help needed from passing comets. The physics backs this up. The Sun's magnetic field is generated by dynamo action deep in the convective zone, where churning plasma acts like a giant electrical generator. The field lines get twisted and tangled by differential rotation, the equator spinning faster than the poles, creating magnetic ropes that eventually burst through the photosphere as sunspots. These are internal processes, driven by the Sun's own rotation and convection. They operate on timescales of days to years, not the few hours it would take for some external influence to propagate from 3I Atlas's position to the solar surface. Gravitationally, the math is brutal. 3I Atlas, even if we assume the largest possible nucleus size of 5.6 kilometers and a density similar to typical comets, maybe half a gram per cubic centimeter, we're talking about a mass around 10 to the 14th kilograms. That sounds like a lot until you compare it to the Sun's 2 times 10 to the 30 kilograms. The tidal force exerted by this comet at 1.36 AU distance would be utterly negligible, lost in the noise of planetary influences and the Sun's own turbulent dynamics. Electromagnetically? Sure, comets can carry charge. They're exposed to the solar wind, which is a plasma, an ionized gas that conducts electricity. Interactions can happen. Comet tails are shaped partly by magnetic forces, but we're talking about inducing an effect on the Sun itself, on a magnetic field generated by processes operating at millions of watts per square meter across a surface area of 6 times 10 to the 18 square meters. The energy scales don't match, not even close. So from the mainstream perspective, the timing is coincidence. Unfortunate, attention-grabbing coincidence that fuels conspiracy theories and makes social media detectives think they've uncovered some cosmic secret, but coincidence nonetheless. The Sun was going to produce AR4294, whether or not 3I Atlas showed up. The fact that a relatively small, distant comet happened to be at perihelion when this active region emerged is no more meaningful than noting what phase the Moon was in or what constellation Jupiter occupied. Except, and here's where the scientific disagreement gets interesting, except the object brightened faster than expected, except its polarization signature is genuinely anomalous, except the chemistry is slightly weird, and except a small but vocal minority of researchers are willing to say, we don't understand everything here. The brightening anomaly is real. Multiple observatories confirmed it. The luminosity curve near perihelion showed a steeper slope than models predicted, based on the object's estimated size and distance. One explanation is that the nucleus is larger than we think, more like 5 kilometers than 300 meters, which would give it more surface area to sublimate volatiles. But if it's that large, other aspects of the observations don't quite fit. The total mass of ejected material, the duration of peak activity, they suggest something smaller, but more active. Another explanation involves composition. Maybe 3I Atlas is unusually rich in super volatile ices, compounds like carbon monoxide or nitrogen that sublimate at lower temperatures than water ice. These would start outgassing further from the Sun, potentially explaining the early brightening. But spectroscopy should have caught stronger signatures of these compounds if they were dominant. The data shows mostly CO2 and water, with organics as minor constituents. A third idea gets into structure. What if the nucleus is porous, fluffy, more like a loosely bound rubble pile than a solid chunk. That could increase the surface-to-volume ratio, allowing more ice to be exposed to solar heating simultaneously. This kind of structure might also explain the weird polarization, if the dust grains being ejected have unusual shapes or compositions inherited from interstellar formation conditions. The polarization issue genuinely bothers people. Several research groups published papers noting the anomaly and struggling to explain it within conventional cometary dust models. One team proposed that the dust contains a high fraction of carbonaceous material with specific optical properties. Another suggested that interstellar radiation and cosmic rays might have altered the surface chemistry of dust grains during their millions of years in deep space, creating compounds we don't typically see in solar system comets. These are all reasonable scientific hypotheses. They don't require exotic physics or conspiracy. They just require that 3I Atlas is a bit different from run-of-the-mill comets, which makes sense given that it formed in a completely different stellar system under potentially different conditions. But then you have the timing question, and this is where some researchers get uncomfortable. Not because they believe in causal connection, but because dismissing correlation too quickly can blind you to real phenomena. The history of science is full of dismissed correlations that turned out to be causations operating through mechanisms nobody had thought of yet. A few brave souls have published papers exploring whether there might be plasma physics effects we're missing. The heliospheric current sheet, the boundary where the sun's magnetic field changes polarity, extends billions of kilometers into space, and creates complex structures. Could a charged object crossing certain regions of this current sheet induce perturbations that propagate back to the sun? The papers are highly speculative and hedged with caveats, but they exist. Others point out that we still don't fully understand magnetic reconnection, the process where magnetic field lines break and reconnect, releasing tremendous energy. This is what drives solar flares. Could external factors, even very weak ones, influence where and when reconnection events occur? Most physicists would say the energy barriers are too high for something as puny as a comet's influence to matter, but we're still refining our models. The disagreement boils down to this. Mainstream consensus says the sun does what the sun does on its own schedule, and 3I Atlas is an interesting but ultimately irrelevant sideshow. The anomalous properties of the comet are noteworthy and deserve study, but don't change the basic picture. A minority view, cautious and scientifically grounded, says we should at least investigate whether there are coupling mechanisms we haven't considered, not because we think a comet can turn on a sunspot, but because science advances by examining the cases that don't fit the model. And then, of course, there are the fringe theories. But we'll get to those, because if you think the scientific disagreement is spicy, wait until you see what the internet has cooked up. Now, we enter the territory where peer review fears to tread, where speculation runs wild, and physics takes a backseat to imagination. This is the realm of fringe theories, alternative science blogs, and late-night YouTube videos with all-caps titles. Some of these ideas are interesting thought experiments. Others are, let's be charitable, creative fiction masquerading as discovery. But they're part of the story, because they reveal how humans respond when confronted with anomalous data and suspicious timing. Let's start with the electric universe, folks. This is a community of alternative thinkers who believe that electromagnetic forces, rather than gravity, are the dominant organizing principle of cosmic phenomena. They argue that mainstream astronomy underestimates the role of electric currents and plasma behavior in shaping everything from planetary orbits to galaxy formation. Mainstream science considers this fringe at best, pseudoscience at worst, because the math doesn't support the necessary charge separations and current magnitudes. But stick with me, because their take on 3I Atlas is fascinating. According to electric universe proponents, the heliospheric current sheet, that genuine plasma structure extending from the sun, is more than just a magnetic boundary. It's an active electrical circuit, a conductor capable of transmitting perturbations across vast distances. When 3I Atlas crossed certain regions of this current sheet, it didn't just passively bathe in the solar wind. It coupled electromagnetically with the circuit, inducing disturbances that propagated along magnetic field lines back to the sun. Think of it like dropping a rock into a pond. The rock itself is small, but the ripples spread. In this analogy, the current sheet is the water, 3I Atlas is the rock, and AR4294 is the splash where the ripples converged. The mechanism requires electric currents, orders of magnitude larger than mainstream physics accepts, which is why scientists dismiss it. But the electric universe community points to the timing and says, explain that away. They can't prove it. The burden of proof in science lies with the claimant, and extraordinary claims require extraordinary evidence. Electric universe advocates have models but lack the observational data and experimental validation that would convince the wider scientific community. So it remains fringe, interesting to consider, but not remotely established. Then there's the heartbeat interpretation, and this one gets weird. Some observers analyzing the light curve of 3I Atlas near Perihelion claim to detect periodic variations in brightness with a regularity that seemed too perfect to be random outgassing. One blog post compared it to a heartbeat, a rhythmic pulse that repeated on timescales of hours. The implication, barely spoken but heavily insinuated, is that this could be an engineered signal, evidence of artificial activity. Before you roll your eyes completely out of your skull, remember that we take this seriously for radio signals. SETI, the search for extraterrestrial intelligence, scans radio frequencies looking for patterns that would indicate technological origin. Why not optical pulses? The answer is, we do look for those too, but extraordinary claims and extraordinary evidence. Remember? The heartbeat in 3I Atlas's light curve is irregular enough, noisy enough, that it's easily explained by natural processes. Comets don't emit light steadily. They sputter and surge as different patches of ice sublimate, as the nucleus rotates, presenting different terrains to sunlight, as dust clouds expand and thin. But the idea took off online. Threads on alternative science forums speculated about artificial probes disguised as comets. Reconnaissance missions from distant civilizations monitoring stellar systems throughout the galaxy. It's a fun idea for science fiction. It makes for engaging speculation. It has approximately zero supporting evidence. Related to this are the chemical signature controversies. News outlets, particularly in regions where science journalism sometimes prioritizes clicks over accuracy, ran headlines linking the detection of methanol and hydrogen cyanide in 3I Atlas's coma to signs of alien life, or biological activity. Let's be very clear here. Methanol and hydrogen cyanide are common in comets. They form through simple chemical reactions in cold interstellar environments. Their presence is interesting for understanding chemistry in space, but it doesn't imply anything biological, let alone intelligent. The confusion arises because these same molecules are also found in biological systems on Earth. Methanol appears in fermenting fruits. Hydrogen cyanide is a key precursor in prebiotic chemistry, the formation of life's building blocks. But context matters. Finding these compounds in a comet is like finding water in a cloud. It's just chemistry, not evidence of thirsty sky creatures. Avi Loeb enters the conversation here. The Harvard astronomer has made a second career out of speculating, always carefully framed as speculation, about the possibility that some interstellar objects might be artificial. He gained fame or notoriety, depending on your perspective, for suggesting that Oumuamua could be a light sail, a thin reflective structure pushed by starlight, explaining its anomalous acceleration. Most astronomers think Oumuamua was just outgassing in ways we didn't detect, but Loeb keeps the alternative hypothesis alive. He's commented on 3I Atlas too, noting its anomalies and suggesting that we shouldn't dismiss exotic explanations too quickly. To be fair to Loeb, he's not claiming it's aliens. He's arguing for intellectual openness, for exploring all possibilities before settling on the comfortable natural explanation. The problem is nuance doesn't translate well to headlines. Scientist says we should keep an open mind becomes Harvard professor claims comet might be alien probe. The Galileo Project, Loeb's initiative to seriously investigate potential technological artifacts in space and atmosphere, would love to get more data on objects like 3I Atlas. They argue, not unreasonably, that we shouldn't assume every anomalous observation has a natural explanation just because natural explanations are statistically more likely. Extraordinary claims require extraordinary evidence. Yes, but you have to look for the evidence to find it. Compare this to Oumuamua, our first confirmed interstellar visitor. That object displayed acceleration that couldn't be explained by gravity alone. The mainstream explanation is outgassing, even though we didn't detect the gas directly. The alternative explanation is that it's artificial, a defunct probe or light sail tumbling through space. The data doesn't definitively rule out either interpretation, which is why the debate continues. 3I Atlas has its own set of anomalies, different ones, but they inspire similar speculative leaps. The rapid brightening becomes energy discharge. The weird polarization becomes non-natural materials. The timing with solar activity becomes deliberate interaction. String enough anomalies together, add a dash of suspicious timing, and you've got a conspiracy theory ready to go viral. Online communities dedicated to exploring these ideas are vibrant. They're not all cranks and conspiracy theorists. Many participants are genuinely curious people with scientific literacy who enjoy exploring what-if scenarios. The problem arises when speculation hardens into certainty, when "this is interesting to think about" becomes "this is what really happened," and scientists are covering it up. There's no cover-up. The data is public. Observatory logs are published. Research papers are available on preprint servers before they're even peer-reviewed. If there was something genuinely anomalous that standard physics couldn't explain, scientists would be all over it. Unexplained phenomena are career makers. Nobel Prizes go to people who overturn paradigms, not to those who confirm existing models. So where does that leave the fringe hypotheses? They're fun. They're thought-provoking. They highlight the gaps in our knowledge and the edges where our models get fuzzy, but they're not supported by the weight of evidence. They require special pleading, overlooking contrary data, accepting anomalies as proof rather than as puzzles to solve through ordinary investigation. Science thrives on skepticism. It demands reproducibility, predictive power, and parsimony, the simplest explanation that fits the facts. Fringe theories often fail these tests, but they serve a purpose. They remind us that science isn't finished, that mysteries remain, and that keeping an open mind doesn't mean believing everything. It means being willing to follow evidence wherever it leads, even if it leads to boring natural explanations. The real question isn't whether 3I Atlas is an alien probe or a cosmic trigger for solar chaos. The real question is, what don't we know about interstellar objects, and how can we learn it? Science hates uncertainty. Well, that's not quite true. Scientists love uncertainty because it's where discovery lives, but they hate having too much of it when they're trying to answer specific questions. And with 3I Atlas, we've got uncertainty to spare. Let's catalog what we don't know, what we need to know, and when we might find out. Because the story of this interstellar visitor isn't over. It's still out there, receding from the sun, and the data collection continues. First, the big one: composition evolution over time. We got great spectroscopic data during perihelion, when the comet was at peak activity. The James Webb Space Telescope's infrared observations, Hubble's visible light measurements, ground-based telescopes with specialized instruments, they all contributed pieces to the puzzle. But those are snapshots. Comets change as they move through the solar system. Volatile ices sublimate in different sequences depending on temperature. The first stuff to go is the supervolatiles like carbon monoxide, then water ice, then refractory materials that only vaporize when you really heat them up. What we need are observations over months, even years, as 3I Atlas continues its outbound journey. How does the coma composition shift? Does the dust-to-gas ratio change? Are there volatile species that only become apparent later, or that shut down as the comet cools? These temporal changes reveal internal structure. A homogeneous nucleus sublimates differently than a layered one. If 3I Atlas formed in an interstellar environment, it might have compositional gradients we've never seen in solar system comets. The European Space Agency's JUICE spacecraft gave us our best close-up images during Perihelion, but JUICE is headed to Jupiter. Its trajectory is now diverging from the comet's path. However, ESA has indicated that full science data analysis from JUICE's observations won't be available until 2026. Space missions generate enormous amounts of data, and processing it, calibrating instruments, removing artifacts, converting raw numbers into physically meaningful measurements, all of that takes time. When that data drops, we'll get refined estimates of the nucleus size, better characterization of the coma structure, and possibly high-resolution spectra that resolve ambiguities in the chemical inventory. JUICE wasn't designed to study comets, but spacecraft are opportunistic. They observe targets of opportunity when geometry allows, and 3I Atlas was definitely a target worth observing. Polarimetry is another gap. We got polarization measurements that showed the anomalous negative values, but those were limited to specific wavelengths and phase angles. What we need is a complete polarization phase curve across multiple wavelengths from ultraviolet through infrared. That would constrain dust grain properties much more tightly. Are we dealing with organic mantles on silicate cores, pure carbonaceous grains, fluffy aggregates with exotic void geometries? Each possibility predicts different polarization signatures. Ground-based telescopes could, in principle, continue making these measurements as the comet fades. The challenge is that 3I Atlas is getting dimmer as it moves away from the sun, and polarimetry requires relatively bright targets to get good signal-to-noise ratios. There's a race against time. Observe now, while you can still detect it, or risk losing the opportunity forever as it fades into the black. Long-term tail behavior is fascinating from a different angle. Comet tails are shaped by two forces: radiation pressure from sunlight pushing dust particles and the solar wind plasma shaping ionized gas. The dust tail is curved, lagging behind the comet's motion. The ion tail is straight, always pointing away from the sun. By monitoring how 3I Atlas's tails evolve, we learn about the dust grain's size distribution and the ionization state of the gas. But here's a subtlety. Interstellar comets spend most of their existence in the cold between stars, exposed to cosmic rays and interstellar radiation fields. This could alter surface chemistry, creating compounds that sublimate or ionize differently than fresh solar system materials. If we see unexpected tail dynamics, it might be evidence of these interstellar weathering effects. The solar activity correlation is a data gap of a different sort. We need more interstellar objects. Sample size of 3, 1I, Oumuamua, 2I, Borisov, 3I Atlas, doesn't let you do statistics. If the next interstellar visitor that reaches Perihelion is accompanied by unusual solar activity, maybe there's something real to investigate. If 10 more pass through with no solar correlation, the 3I Atlas timing becomes obvious coincidence. New telescope surveys are coming online that will dramatically increase our detection rate. The Vera C. Rubin Observatory in Chile, when it begins full operations, will scan the entire visible sky every few nights. Its sensitivity and survey speed mean we'll likely detect dozens of interstellar objects per year instead of one every few years. That sample size will let us characterize the population, understand what's typical and what's genuinely anomalous. Seismic data presents its own challenge. Earthquake catalogs are extensive, but proving or disproving a correlation with specific astronomical events requires careful, statistical analysis. You need to define your temporal windows, decide what magnitude range you're examining, control for spatial clustering and tectonic context. It's easy to find apparent patterns in noisy data if you're not careful about methodology. What researchers need is a pre-registered analysis plan, something decided before looking at the data, to avoid the pitfalls of pattern seeking. Define what would constitute evidence for a real correlation versus random chance. Apply the same analysis to periods when no interstellar objects were present. Only if you get a statistically significant difference can you claim something real. Nobody's done this rigorously for 3I Atlas yet, partly because it requires collaboration between astronomers and seismologists, fields that don't typically overlap. But if someone wanted to settle the question of whether the earthquake uptick was real or imagined, that's the methodology to use. Theoretical models need work too. We have equations describing comet outgassing, plasma interactions, heliospheric structure, but they're approximations. Real plasmas are messy. They develop instabilities, form structures, conduct electricity in ways that simplified models miss. There's a reason we build supercomputers to simulate these systems, and even then, we're making compromises. If someone wanted to seriously test whether a charged object at 1.36 AU could influence solar magnetic activity, they'd need to run high-fidelity magnetohydrodynamic simulations of the entire heliosphere, including the sun's convective zone, the photosphere where sunspots form, the solar wind, the heliospheric current sheet, and the comet's plasma environment. That's computationally expensive, and unless there's strong motivation, i.e., evidence that can't be explained otherwise, it's not a priority for research funding. The gaps in our knowledge are substantial, but that's normal in science. Every new phenomenon, every anomalous observation opens more questions than it answers. That's frustrating for people who want certainty, who want to know right now whether 3I Atlas did something mysterious or was just a coincidentally timed comet with unusual but explicable properties. The good news is that uncertainty is temporary. More data will arrive. JUICE's full analysis in 2026. Continued monitoring as the object recedes. Future interstellar visitors providing comparative cases. Advances in plasma physics modeling and observation techniques. Science is a ratchet. It moves forward unevenly, sometimes slowly, but always toward better understanding. The data gaps surrounding 3I Atlas will fill. The question is whether they'll fill with boring confirmation of standard comet models, or with something genuinely new that forces us to expand our understanding of how matter and energy interact in the cosmos. Either outcome is valuable. Confirmation means our theories work, which is always satisfying. Discovery means we get to be wrong in interesting ways, which is how knowledge grows. Let's zoom out. Because while 3I Atlas has been capturing our attention with its suspicious timing and weird properties, the rest of the universe hasn't paused for breath. Major discoveries are cascading from observatories and space missions at a pace that would have seemed like science fiction a generation ago. One of the most significant recent developments comes from the Subaru telescope in Hawaii. This 8.2-meter monster has been conducting deep surveys of star-forming regions, and the data is rewriting our understanding of planetary system formation. Astronomers have identified populations of brown dwarfs, those failed stars too small to ignite hydrogen fusion, but massive enough to be interesting, existing in regions where planet formation is actively occurring. The boundary between planet and brown dwarf has always been fuzzy. Traditionally, we say objects above about 13 Jupiter masses are brown dwarfs because they confuse deuterium, while anything below is a planet. But formation mechanism matters too. Did the object collapse from a cloud like a star, or accrete in a disk like a planet? Subaru's observations show both processes can create objects in the same mass range, which complicates our taxonomy. Why does this matter for understanding interstellar objects? Because the same processes that form brown dwarfs and massive planets also generate debris. When young stellar systems are chaotic, with giant planets migrating and gravitational interactions flinging matter around, you get ejections. Small bodies are kicked out at high velocity, becoming interstellar wanderers. The more we understand about planetary system dynamics in other stellar systems, the better we can interpret objects like 3I Atlas when they show up in our neighborhood. Speaking of neighborhoods, international collaboration in space science is evolving rapidly. China and Brazil recently announced a joint space laboratory initiative focused on astronomy and Earth observation. This partnership brings together Chinese launch capabilities and satellite technology with Brazilian scientific expertise and equatorial launch site advantages. For the global scientific community, this means more eyes on the sky, more data being collected, and more opportunities for collaborative research. There's a geopolitical dimension too, but let's keep the focus on science. More countries with advanced space capabilities means more diversity in research priorities, more redundancy if missions fail, and more likelihood that interesting phenomena get observed from multiple perspectives. When China's space station hosts astronomical instruments, or when Brazil contributes ground stations and observatories, the whole field benefits. Stellar explosions are teaching us new things constantly. Type Ia supernovae, the standard candles we use to measure cosmic distances and map the universe's expansion, turn out to be less standard than we thought. Recent observations have identified multiple pathways to these explosions, each leaving slightly different imprints in the spectrum and light curve. This has implications for cosmology, for our estimates of the universe's age and expansion rate, but it also connects to interstellar chemistry. When stars explode, they scatter heavy elements across space. Carbon, oxygen, silicon, iron, all the atoms heavier than hydrogen and helium get forged in stellar cores and explosive events, then seeded into interstellar clouds where new stars and planets form. Every atom in 3I Atlas, every molecule in its coma, was once inside a star that died billions of years ago. Stellar explosions are the ultimate source of cosmic diversity. The organic chemistry angle is particularly fascinating. Interstellar comets like 3I Atlas carry complex carbon-bearing molecules, and there's a long-standing question about how organic complexity arises in space. Experiments show that simple molecules like water, carbon monoxide, and ammonia, frozen onto dust grains and irradiated by ultraviolet light and cosmic rays, will spontaneously form more complex species, including amino acids, the building blocks of proteins. This isn't life, it's prebiotic chemistry, the chemistry that might have preceded life's origin on Earth and presumably elsewhere. But it's profound. It means organic complexity is built into the fabric of the cosmos, not some rare accident confined to a few lucky planets. Every comet carries a chemistry lab, experimenting with molecular combinations for millions of years before potentially delivering those molecules to planetary surfaces. Recent findings have detected complex organics in the atmospheres of exoplanets, planets orbiting other stars. The James Webb Space Telescope has revolutionized exoplanet characterization by analyzing how starlight filters through planetary atmospheres during transits. We're detecting water vapor, carbon dioxide, methane, and in some cases, hints of even more complex species. None of this is evidence of life, but it's evidence that the chemical ingredients for life are common. Connect this back to interstellar objects. They're messengers carrying samples of chemistry from other stellar systems. When we analyze 3I Atlas's coma composition, we're not just studying one comet. We're sampling the chemistry of whatever system it formed in billions of years ago. Different stars create different conditions. A comet forming around a low-mass red dwarf will have different ice chemistry than one forming around a sun-like star or a massive blue giant. Solar system dynamics research continues revealing how chaotic planetary evolution can be. Simulations show that in the early solar system, there were likely additional planets, ice giants that got ejected entirely through gravitational interactions with Jupiter and Saturn. The NICE model, a leading scenario for early solar system evolution, proposes a period of instability when the giant planets migrated, reshuffling the entire architecture and scattering countless small bodies. Some of those bodies stayed in the solar system, becoming the Kuiper Belt and Oort cloud. Others achieved escape velocity, becoming interstellar wanderers. This process is probably common. Every stellar system with giant planets goes through periods of chaos. The galaxy is full of ejected comets, asteroids, and possibly even rogue planets, all drifting through the dark. When we detect interstellar objects, we're seeing the cast-offs from this universal process. The question is, what fraction of interstellar objects are simple comets, and what fraction might be more exotic? Failed planets, fragments of collisions, material from stellar systems with unusual compositions, or evolutionary histories? We need larger sample sizes to answer this. Upcoming missions and facilities promise to provide those samples. The Vera C. Rubin Observatory will begin full science operations soon, and its legacy survey of space and time will detect faint, fast-moving objects that previous surveys missed. Estimates suggest we'll find anywhere from tens to hundreds of interstellar objects per year once Rubin is operational. The Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission scheduled to launch later this decade, will have a field of view 100 times larger than Hubble's, perfect for surveying large areas of sky and catching transient events. Between ground-based and space-based assets, we're entering an era of astronomical data overload in the best possible way. All of this context matters for understanding objects like 3I Atlas. They're not isolated curiosities. They're part of a larger picture of how matter moves through the galaxy, how chemistry evolves in space, and how planetary systems form and evolve. The weird properties of one interstellar comet might seem like a trivial mystery, but solving it could illuminate fundamental processes affecting billions of systems across the Milky Way. We've traveled from a specific date and a suspicious timing through the strange properties of an interstellar visitor, past scientific disagreements and fringe speculations, into the data gaps and broader context of modern astronomy. Now, it's time to synthesize, to draw the threads together and ask, what have we actually learned? 3I Atlas reached Perihelion on October 29, 2025, staying a comfortable 200 million kilometers from the Sun. Shortly after, the Sun erupted with AR4294, a massive sunspot complex and associated flare activity. Reports of increased seismic activity on Earth followed. The timing is documented. The correlation is real. The causation is, at best, unproven, and at worst, physically implausible. Science demands that we separate correlation from causation. The Sun was already in an active phase of its cycle. Demonstration. Sunspots occur during solar maximum without any help from passing comets. Earthquakes happen constantly on a geologically active planet. Finding a pattern in the noise is what human brains do brilliantly, but it doesn't mean the pattern is meaningful. Yet, 3I Atlas remains genuinely interesting, independent of the solar timing. Its rapid brightening near perihelion exceeds model predictions. Its polarization signature is unlike any other observed comet. Its chemistry shows subtle differences from native solar system comets. These are real scientific puzzles worth investigating. The most likely explanation is that interstellar objects formed in different environments carry different properties. Spending millions of years in the cold between stars, bombarded by cosmic rays and interstellar radiation, could alter surface chemistry and dust grain structures in ways we haven't fully characterized. As we study more interstellar visitors, we'll build a library of their properties and understand the range of possibilities. The fringe hypotheses, the electric universe coupling mechanisms, and artificial probe speculations. They're entertaining thought experiments, but lack the evidential support to be taken seriously. Science isn't closed-minded, it's evidence-demanding. Show me the data that can't be explained otherwise, and I'll happily consider exotic explanations. Until then, natural processes remain the most parsimonious interpretation. Looking forward, the data releases we're anticipating will help clarify several mysteries. JUICE's full science data in 2026 should provide refined physical characterization. Continued ground-based monitoring will track composition evolution as the comet recedes. Future interstellar object detections will give us comparative cases to understand what's typical and what's truly anomalous. The Vera C. Rubin Observatory represents a step change in our detection capabilities. When it's fully operational, surveying the entire visible sky every few nights will shift from interstellar objects are rare curiosities to interstellar objects are a statistical sample we can analyze. That's when we'll really start learning. Every new data point constrains theory space. Every additional interstellar visitor tells us something about planetary system formation, material evolution in the galaxy, and the diversity of small bodies in the cosmos. If the next few interstellar comets all show similar polarization anomalies, maybe that's a signature of interstellar weathering. If they're all different from each other and from solar system comets, maybe formation environment is highly variable. If they cluster around certain compositions, maybe stellar system chemistry has dominant modes. The earthquake correlation question can be settled with proper statistical methodology. Pre-register an analysis plan. Collect seismic data around future perihelion passages of interstellar objects and compare rates to background levels using rigorous statistical tests. If no correlation emerges across multiple events, the 3i Atlas timing was coincidence. If a pattern persists, then we have something genuinely strange to investigate, and mainstream science would eagerly do so because unexplained phenomena are career gold. What this story ultimately teaches us is that science thrives on careful investigation, not sensationalism. The internet loves breathless headlines about terrifying cosmic mysteries and government cover-ups. Reality is more nuanced and, honestly, more interesting. We have a genuinely unusual object with properties we don't fully understand yet. That's exciting. That's discovery in progress. But it doesn't require abandoning physics or invoking alien technology. The beauty of science is its self-correcting nature. Propose a hypothesis, test it against data, refine or reject based on results. The process is messy, involves human egos and institutional inertia, but over time it converges on truth. When we don't know something, we say we don't know and work to find out. When we do know, we state it with appropriate confidence levels and uncertainties. 3i Atlas has expanded our understanding whether or not it did anything to the sun. We've learned that interstellar comets can have unusual dust properties. We've been reminded that solar activity is complex and not entirely predictable. We've seen how timing coincidences can fuel speculation and conspiracy theories. We've identified data gaps that future observations will fill. The object is still out there, receding into the dark between stars. It'll carry its mysteries with it, gradually fading from our telescopes until it's once again invisible. One more wanderer in the galactic void. But we've captured its moment of visibility. We've measured its light, analyzed its chemistry, imaged its coma. That data will persist, archived in databases and papers, ready for future researchers to mine when new theoretical insights make old data suddenly relevant again. Did 3i Atlas trigger solar chaos? Almost certainly not. Did it teach us something about the diversity of small bodies in the galaxy? Absolutely. Did its suspicious timing make for a compelling story that highlights the difference between correlation and causation? You're reading 7,000 words about it, so yes. The universe is full of actual mysteries that don't require embellishment. Dark matter that outweighs normal matter, but remains undetected except through gravity. Dark energy accelerating the expansion of space itself. The formation of the first stars and galaxies in the early universe. The potential for life beyond Earth. These are questions where our ignorance is vast and humbling. An interstellar comet with weird dust properties doesn't rank among the deepest cosmic mysteries, but it's a piece of the puzzle. Every observation adds pixels to our picture of reality. Every anomaly resolved either confirms our theories or forces us to expand them. That's how knowledge grows, incrementally, sometimes frustratingly slowly, but inexorably. So when you look up at the night sky, know that there are objects passing through right now that we haven't detected yet. Interstellar wanderers on their own trajectories, carrying chemistry from distant stellar systems, potentially bearing properties that will surprise us when we finally observe them. The galaxy is in motion, a vast ecology of matter and energy, where even small visitors can teach profound lessons if we pay attention. 3i Atlas came and went, leaving more questions than answers. That's perfect. That's exactly what science needs. Questions drive investigation. Investigation reveals patterns. Patterns suggest mechanisms. Mechanisms predict new observations. New observations test theories. And the cycle continues, pushing the boundary of knowledge outward into the unknown. Did it short-circuit the sun? No. Did it shake the Earth? Probably not. Did it capture our imagination and remind us that the cosmos still holds surprises? Absolutely. And that, ultimately, is what makes it worth discussing. The universe doesn't owe us comprehensibility. It doesn't care if we understand. But we're a species that looks up and wonders, that builds instruments to see farther and measure more precisely, that takes scattered photons and weaves them into stories about our cosmic neighborhood. 3i Atlas is one of those stories. Not the terrifying tale the headline promised, but something arguably better. A real scientific investigation playing out in real time, with gaps and uncertainties and disagreements and gradual progress toward understanding. That's the actual process of science, stripped of mythology and shown in its messy, human, ultimately triumphant form. The next interstellar visitor is already on its way. We just don't know it yet.